Hello, I'm Stefano Parisi, Research Fellow at the Design Department of the Politecnico di Milano. In this lecture, you will go through examples of smart materials that can be applied to the fashion context, and you will be introduced to the related opportunities and challenges. The aim of the lecture is to inspire you for a meaningful integration of smart materials for textile hybridization. Today, we live in a world where the artifacts we use and wear in our everyday life are becoming more and more embedded with smartness. Smartness is the quality of an object to adapt to circumstances by reacting to different stimuli. To respond to this urgency, we need to apply materials able to implement and support smartness. These are called smart materials, a relatively new expression used to identify materials that have changeable properties, in opposition to traditional materials that are latent. They can change some features, like shape or color, in response to physical or chemical influence from the environment or from the user's body. For example, pressure and mechanical stress, electric or magnetic field, light, temperature, moisture, pH, chemical elements and compounds. The behavior of the materials depends on the external stimuli and is reversible. This means that in the majority of cases, when the material is excited by the stimuli, the behavior is simultaneous. When the source is removed, the material stops to perform and returns to its original condition, and this can be repeated many times. Usually, the behavior is programmable, meaning that such materials are engineered to respond to a predetermined spectrum. There is a wide range of smart materials. They can be classified according to their behaviors. The most relevant categories for fashion are shape-shifting and color-changing. Shape-shifting means that after a deformation, materials can return to their original shape when triggered by heat or electric current. Applications of this category include shape memory alloys, that are metal alloys commonly mentioned as nitinol, flexinol, and muscle wires. Frequently, they are available in the shape of sheets, springs, or wires. These can be integrated into textiles by interweaving them with traditional fibers. The second category is color changing. These materials change their color in response to external stimuli. Thermochromic responds to changes in temperature. Photochromic responds to changes in light condition. Electrochromic responds to electric fields. They are frequently available in the shape of pigments, inks, and coatings that may be applied to any surface, from polymers to glass, from paper to textile. Besides these two categories, other smart materials are light-emitting smart materials and electricity-generating smart materials. The first ones emit lights due to the excitement of their molecules and are classified as fluorescent, phosphorescent, and electroluminescent materials. Instead, the most known ones among electricity-generating materials are piezoelectric ceramics and polymers. On applying mechanical stress to these materials, they generate an electric current and vice versa. It is often possible to combine several materials with smart properties together to create complex changing behaviors. This combination defines systems that are called smart materials composites. Also, this combination entails the hybridization and cooperation of smart materials and electronic components into hybrid material systems in order to increase the smart qualities of the final product. This concept frames the phenomenon of interactive, connected, and smart materiality, known as ICS. Smart materials have been applied in a range of design sectors up to fashion. They can be combined with traditional materials and electronic components to obtain sensing and responsive wearables and textiles. Smart textiles play a significant role in the fashion sector and can be defined as textiles that can sense and respond to changes. They may be divided in three classes in chronological order: passive smart textiles, active smart textiles, and very active smart textiles. Passive smart textiles are the first generation of smart textiles found in clothing, which can only sense environmental or body conditions. The second generation is active smart textile, which have both sensors to detect and actuators to react, by changing their features according to an environmental or body stimulation. Lastly, very active smart textiles, the third still conceptual generation of smart textiles, can sense, react, and adapt themselves to the given circumstances due to the application of dedicated softwares, such as face recognition ones, with the potential of integrating artificial intelligence and machine learning. The application of such materials into fashion unfolds many opportunities both from an aesthetic and functional perspective. Smart materials enhance the aesthetic enjoyment by triggering the effect of surprise and by creating multisensory experiences. Smart materials have also the transformative role of making invisible data tangible and information more accessible. Examples of pattern-revealing and color-changing clothes reacting to pollution or to the pH of the rainwater demonstrate how smart materials may trigger behavior change, enabling users to behave more awarely and proactively. Smart textiles and wearables may have a huge impact on sport and healthcare industries. Indeed, they can be used to monitor and support body activities. For example, they can be used for health prevention and rehabilitation. They also allow wearables to constantly adapt to the user's needs, as demonstrated by the example of a jacket that shrinks in warmer environment or the one of a garment adapting to the user's diaphragmatic breath. From a sustainability perspective, the integration and partial substitution of traditional electronic components and energy supplies with smart materials lead to the optimization and reduction of energy flows. This is the case of piezoelectric materials as an alternative for batteries or thermochromic coating as an alternative to technological interfaces. Conductive materials support and enable the interconnection between the components of a system, substituting traditional wires and cables. These are mainly graphite, active carbon, and silver, and can be found in the shape of conductive fibers, woven or knitted into textiles, threads, printed circuits, paints, and coating. By the seamless combination of electronics, conductive and resistive materials, and smart materials into textile, it is possible to obtain almost limitless results, such as touch and pressure-sensitive textiles. By introducing smart materials, new tasks and challenges for designers emerge. Designers must ensure that in achieving what is technically feasible, the well-being of people is preserved, and are respected the requirements of wearability, comfort, warmth, softness, flexibility, and maintenance, including washability. The design of smart textiles combines traditional methods with advanced technology, creating a new area for fashion designers to explore, one in which the capability of the designer to modify the characteristics of the textiles can be made by both physical manipulation and digital technology. Another challenge regards sustainable fashion, the use of non-toxic renewable, and biodegradable materials is a challenge for smart materials development. The integration with biodegradable materials and fibers may allow the separation of components. An example of experimentation is a conductive bioskin made by growing bacterial cellulose with conductive compounds. In this respect, biological organisms can also be used as biosensors and bioactuators to replace synthetic ones. This is the case of BioLogic, a textile which uses the mechanical behavior of nattobacteria deposited on portions of textiles to respond to moisture. The bacteria's body enlarges with humidity, allowing the textile to change shape. Other examples of biosensors are organic primitives, pH-reactive organic materials used for sensing, actuating, and interacting, or the use of bioluminescent organisms for performing light-emitting behaviors. Researchers and designers are exploring the smart behaviors of traditional materials supported by digital manufacturing and parametric design, such as organic pulp-based surfaces and fibers reacting to moisture. In conclusion, during this lecture, we have explored the potentials and limits of smart materials for fashion. These include market-ready products and conceptual experimentations that will redefine our near future.